This is the second part of a three-part video in problems and solutions for indeterminate forms and Looptails Rule. The first 9 problems were discussed in part 1, so we start with problem 10 in this video. I won't have a chance here to talk about the background behind indeterminate forms and Looptails Rule, but I've discussed those in details in a separate video, and I have put the links in the video description. So our first problem in this video, problem 10, involves the limit as x goes to 1 of this fraction here. Notice that as x goes to 1, natural log goes to 0, and the square root of x goes to 1. So we get a 0 over 0 expression, denominator being 1 minus 1. Being 0 over 0, that means we have an indeterminate form, and therefore we can use the Looptails rule, which says take the derivative of numerator and denominator separately. Derivative of the natural log of x is 1 over x in the numerator. Square root of x, of course, is x to the power 1/2. So its derivative is 1/2 x to the negative 1/2. Now, as x goes to 1, in the numerator we get 1 over 1. In the denominator we get 1/2, 1 to the negative 1/2. And 1/2 to the negative 1/2 is 1, so that's just 1. 1 divided by 1/2 will be 2, and that's our limit for this quotient. Using a pretty similar type of calculation here, with the except that 1/2 is replaced with any positive real number p. And working through this, you get the same. We get this answer down here, which is kind of neat. In problem 11, we take the limit as x goes to 1 plus of a fraction that looks a lot like the one in problem 10, except that in this problem, the entire x minus 1 is under the square root. As x goes to 1 plus, meaning x goes to 1 from the right-hand side, so x is bigger than 1, and the square root of x minus 1 is defined. So other than that, x goes to 1 plus simply means x goes to 1. Natural log of 1 is 0. Square root of 1 minus 1 is 0, so we get 0 over 0. It is an indeterminate form of the type we can apply Looptails rule to. Quotient form. The derivative of top ln of x is 1 over x. Derivative of x minus 1 square root is x minus 1 quantity to the power 1/2, and its derivative therefore is 1/2 times x to the minus 1 to the minus 1/2. In order to take x limit as x goes to 1, it's more convenient if I write everything with a positive power. So let's take that to the numerator, write it as x minus 1 to the plus 1/2. That x comes down to the numerator, that x comes down to the denominator, and we get this expression. Now, if x goes to 1, I get 1 over 1 to the power 1/2, and that's just 0 to the power 1/2. So everything drops down to 0. The limit in problem 12 is a little bit different. We are looking at the limit as x times ln of x as x goes to 0 plus, again 0 plus, so that x is bigger than 0 from the right, and natural log is well defined. As x goes to 0 from the right, the natural log goes to negative infinity, something you can check out on a calculator or computer in case you don't remember, but maybe just draw a graph, see what happens near 0 from the right. So anyway, we get 0 times infinity indeterminate form. This is a product indeterminate form, which we change to a quotient in the usual way. There's 2 ways of doing it. Here's the way that works best here. X times ln of x, written as x divided by 1 over x. both of the numerator and denominator going to infinity, gives us infinity over infinity. This is a quotient indeterminate form. L'Hopital rule applies to that. Derivative of ln is 1 over x. Derivative of 1 over x, which is x to the minus 1, is negative x to the minus 2. Write everything with the positive power. And notice that you get a cancellation. What's left is minus x, limit of minus x as x goes to 0 plus is 0. And that's the answer. In problem 13, we want to show that this limit over here comes out 0. And to do this, let's first figure out what type of an indeterminate form this will turn out to be. Notice that as x goes to 0, natural log goes to 0, and that means ln of x squared goes to infinity. Ln of x goes to infinity, and so its square also goes to infinity. But as x goes to 0, e to the negative x is 1 over e to the x will go to 0 because the denominator e to the x becomes infinitely large, which means therefore that we get 0 times infinity, an indeterminate form in the product, as a product, which we need to turn into a quotient. In this case, it's fairly straightforward. Just write e to the x as 1 over e to the x and get a fraction right off the bat. Now, applying L'Hopital rule, the numerator derivative of ln of x squared, just the chain rule application, straightforward application of chain rule. We get derivative is equal to 2 times the ln of x to the 1 times the derivative of ln of x, which is 1 over x. Derivative of e to the x in the denominator is itself unchanged. Let's put that x down in the denominator and get this expression. Notice that as x goes to infinity, ln of x and the denominator all go to infinity. So we have still an infinity over infinity form. And apply L'Hopital rule again to this last expression. Derivative of 2 ln of x is 2 times 1 over x, or 2 over x for short. Derivative of x e to the x is a product rule application. Derivative of x is 1 times e to the x, so this should actually be e to the x, plus the x times derivative of e to the x, which is just e to the x. Now, as x goes to infinity, the top goes to 0, and the denominator, the whole thing goes to infinity, and that's about as 0 gets, so the answer is 0, just as we wanted to show. In problem 14, we are taking the limit of a difference of fractions as x goes to 1 from the right-hand side, so that ln of x and 1 over x, the minus 1, are both positive and well-defined. As x goes to 1 plus, ln of x goes to 0 because ln of 1 is 0. So 1 over that goes to infinity. 1 over x minus 1, 1 over 0 goes to infinity as well. So we get an infinity minus infinity indeterminate form. We can't apply L'Hopital's rule to that, but maybe if we combine the two fractions, we get something to which we can apply L'Hopital's rule to. Here's what the two fractions combine as, with common denominator and all that. As x goes to 1 plus, x minus 1 goes to 0, natural log of 1 is 0, so numerator is 0. Down here, 1 minus 1 is 0, and natural log of 1 is 0 as well. So we get 0 over 0. That's the quotient indeterminate form, and we can apply L'Hopital's rule to it. What we get if we use, we take the derivative of numerator, we get 1 minus 0 minus 1 over x. Down below, we use the product rule. Derivative of x minus 1 is 1 times the second ln of x plus the first x minus 1 times the derivative of second ln of x is 1 over x. Let's write this up in a tidy way. And notice that as x goes to 1, 1 minus 1 over x goes to 0. Natural log drops to 0 as well. And here we get 0. So we once again end up with 0 over 0. Applying Looptails rule again. Thinking of 1 over x as x to the negative 1. Its derivative comes out minus x to the minus 2. And notice that x to the minus 2 is 1 over x squared, and this minus cancels that minus after being multiplied. Down below, natural log of x has derivative 1 over x, and 1 minus 1 over x, just like we saw, is 1 over x squared as a derivative. Now, if I put x equal to 1, I get 1 over 1 squared, which is 1, and down below 1 plus 1, so we get the answer to the problem 1/2. In problem 15, we are looking at the limit as x goes to infinity of a difference once again. The first term is the square root of x squared plus 6x as x goes to infinity. Inside the square root goes to infinity as x goes to infinity, and when we take a square root of an infinitely large quantity, again we get infinity. And of course x goes to infinity, so here again we have, just like the last problem, an infinity minus infinity indeterminate form. Cannot apply to this Looptails rule, so we have to somehow get this difference to come out a quotient. For differences involving the square roots, we multiply and divide to keep the expression unchanged by what we call the conjugate, which is basically the same thing as the difference, but with the sum changed to plus. This expression will simplify our original expression and gives us a quotient. So here we are, here is the given expression. We multiply by the conjugate, divide by the conjugate, that way the expression does not change in value. In the numerator, I have let's do it this way, I have a difference a minus b multiplied by a plus b, and when we multiply that out, everything comes out a squared minus b squared. A squared is x squared plus 6x, b squared is x squared, and you'll notice that x squared and minus x squared add up to 0 and leave us with 6x in the numerator. In the denominator, we leave everything the way it came out to be. We have a quotient. As x goes to infinity, which is what we are interested in, so let's go back here. You notice that 6x goes to infinity. The denominator certainly goes to infinity. So now we have an infinity over infinity to which we can apply Looptails rule. Although that's perfectly valid, it's probably a good idea to use an alternative method if we can. And in this case, we can use a little bit of algebra. And that way we avoid taking the derivative of the square root. This is square root here, because that turns out to be a little bit messy. So the simplification, I mean, you can do it by Looptails rule and see what you get. You should get pretty much the same answer, you just work a little harder. But what I do instead here is I divide the numerator and denominator by x. That way I'll cancel the x's and I get and I get this down here after I split the fraction into 2. X over x is 1, and then I'll take that x up inside the square root, and that gives me 1 bigger square root of x squared plus 6x divided by x squared. And that simplifies. I split this. X squared over x squared is 1. And 6x over x squared is just 6 over x. So we end up with this expression. Now we don't have an infinity over infinity anymore, but we have a simpler expression. And we see if we can work this out directly. Take the limit directly. X goes to infinity. 6 in the numerator is unchanged, but 6 over x in the denominator goes to 0. And we are left with 6 over the square root of 1 plus 0 plus 1. And that, of course, adds up to 2. And 6 over 2 is 3. So that's the answer to this problem. I'll end this video by leaving you a couple of limits of similar type to figure out with different answers, of course, that you can write in the comments. And I'll go over more problems and solutions in part 3.